we're given an integral from 0 to positive infinity of e to the minus ax minus e to the minus bx over x dx. And given a and b are both positive. And to calculate this integral, we will first prove this lemma. If a function is continuous over interval from 0 to positive infinity, inclusive of 0, then and if the limit of f of x as x approaches positive infinity exists, denoted as f of positive infinity, or L, or whatever, and it is a finite number, then we have the following result. The integral from 0 to positive infinity of f of ax minus f of bx over x dx is equal to exactly f of 0 minus f of positive infinity, that is the limit as x approaches positive infinity, finite number, times log of b over a. And so we're going to first we will, of course, we will use the lower bound with delta, upper bound use capital A, right? So delta all the way up to capital A. In the end, we will let delta approach 0 and we will let capital A approach positive infinity. But for now, let's just fix them. So I want to calculate this definite integral, first of all. Right, just a normal Riemann integral. Still copy down f of ax minus f of bx over x dx. And of course, we're going to break it apart into two different integrals. So from delta to capital A of f of ax over x dx minus integral from delta to capital A of f of bx over x dx. Perhaps I'll just write it into, denote it as I1 plus minus I2. And for I1, we're going to make a change of variable. All right, so for I1, we're going to let ax equal to t. Then, of course, dx is equal to dt over a. Also change the boundaries. So this time I is equal to the integral from when x is equal to delta, t is equal to a times delta. And also I have a times capital A as my upper bound. So the integrand this time is it's going to be f of t. So x becomes t over a, right? T over a. T over a, the bottom. And so that is equal to just put a on the top. T still stays at the bottom. Right, this time a should sit on the top. And because dx becomes dt over a, right? So the over a and a sits on the top, they just cancel out. So I have 1, right? So this is what I have exactly. So no more a's, right, in this integrand. So this is neat. So likewise, what's I2? Right, for the same reason, I'll just skip over the steps. For the same reason, I2 is equal to exactly the definite integral from, likewise, here I use A. For I2, I just use B, right? The same idea, right? Exactly the same. So B times delta all the way up to B times capital A. The same integrand, f of t over t dt. Right? So I just have to work out their difference. So to work out their difference, let me first draw a picture. So first of all, perhaps 0, right? And remember, delta is small enough, right? Let's make it small. So A times delta. Perhaps here. Perhaps I'll just assume that 0 is less than A is less than B, without loss of generality. Because if A was equal to B, what do we have? we have 0 on the top, right? Integral becomes just 0, so that's trivial. So we can just assume this condition, right? So I have a times b times delta. Where is b times delta? Perhaps here, a little bit bigger than this point, right? So where is little a times capital A? Somewhere here. And also little b times capital A, somewhere here. Right, for the same reason, because b is bigger than a, so b times a is bigger than a times a, right? So basically, I want to work out the area under, perhaps, that's the curve of my function f, right? So the area under the curve. So I'm trying to work out this area minus that area, right? So what does this represent, right? So from this point up to this point, right? So that is area under the curve from this point up to this point, right? That is this section. How about that? That is from this, so from this point up to that point, right? So basically, I'm trying to work out the so this area minus this area, right? So this area minus this area. So when I take their difference, say the middle area is their common, is their overlap. So it'll just be cancelled out, right? So basically, I'm just trying to work out this area minus this area, right? So the integral from this to this minus the integral from this to that. Right, so basically I'm trying to, so I1 minus I2 is basically equal to the integral from A delta up to B delta of f of t over t dt minus the integral from this point to that point, right? AA, BA. Same thing, ft over t dt, right? So what do I do now? Remember, like I said, we're going to let delta approach 0 and going to let capital A approach positive infinity. So before we do that, let me just use the theorem of the mean value of integration. Right? So as long as we have a product of two functions, first function f of t, second function 1 over t, right? As long as they're both continuous, are they? Yes, they're both continuous. And of course, the second function 1 over t, is its sign, is it always consistently positive over this interval? I think so, yes, because A and B are both positive, then delta is also positive. We're going to let delta approach 0 from the right-hand side of 0. Right, so, of course, 1 over t stays consistently positive over this interval. And, of course, over this interval, 1 over t stays consistently positive. So that we can apply the theorem of intermediate value of integration. Right? We can just take out first function f of t out of the integral. So for perhaps let me just rewrite it into this integral is equal to perhaps I3, and that integral is equal to I4. Right? So for I3, what do I have? I3, like I said, I'm going to take out f of t and replace t with c. And f of c times the integral from a delta up to b delta of dt over t. And at the same time, c is a point that's in between, in the open interval of this interval, right, a delta b delta. Just some fixed point inside this open interval, and f of c. And likewise, I4 is equal to, take out f of t, I have f of eta, where eta lives inside the open interval of this interval, a, capital A, and b, capital A, times the integral from a, capital A, b, capital A, dt over t, right? So in the end, I should have, so this is what log of t evaluated from this to that, right? So basically I have log of b delta minus log of a delta, right? Logarithm rule, I have log of b delta over a delta. Delta cancels out. I have log of b over a times f of c. Right? F of c times log of b over a. Right? And for the same reason, minus f of eta times, for the same reason, right? Capital A just cancels out. I still have the same thing, log of b over a. Right? Then we're going to determine, because like I said, we were going to let delta approach 0 from the right-hand side and let capital A approach positive infinity. So when delta approaches 0 from the right-hand side, what's going to happen? Right? What's going to happen is that, because A and B are both fixed, right? So delta becomes closer and closer to 0, right? So B times delta will, of course, get closer and closer to 0. So will B times delta, right? They both get very close to 0. So since c lives just, c is just between this point and that point, right? It's kind of squeezed in between those two guys. So as those two guys approach 0, c will also approach 0, right? Obviously. So, but the question is there a limit when c approaches 0? Yes, because f is given to be continuous in this, including 0 in this interval, right? So limit not only exists, but it is equal to the functional value at 0, right? So like I said, it's going to, perhaps let me just write, it's going to approach, I'm just going to extract log, first of all, I'm going to extract log of b over a out here. Then this guy will approach f of 0. And then this guy, right, as capital A approaches positive infinity, right? So this guy is going to get very, very far away, right? So will this guy. They both approach positive infinity, and eta is kind of squeezed in between those two guys. So eta will automatically also approach positive infinity as well, right? So like I said, we assume that the limit exists as x approaches positive infinity, denoted as this, right? So we immediately have minus f of positive infinity, that is a finite number, as delta approaches 0 from the right-hand side and as a approaches positive infinity. Now I'm done with the proof of this lemma. So it's called so this type of integral is called Frullani integral. So we're going to check if our function satisfies the given conditions in order to apply this lemma. So f of x is equal to e to the minus x, right? Since we're gonna say f of ax bx, right? Ax bx, so we're gonna let it equal to e to the minus x. So the question is f continuous over this interval? Of course it is. Then is f of x, is this limit, does this limit exist, right? So as x approaches, yes, as x approaches positive infinity. So this function will, of course, approach, because this is equal to 1 over e to the x. As x approaches positive infinity, or the bottom is going to approach positive infinity. So the whole thing is going to approach just 0. All right. So what is f of 0? F of 0 is easily e to the 0. That's just 1. Right? So according to our formula, our integral should equal to exactly, right, we have exactly this form. So our integral is, right, f of 0 minus f of positive infinity, right? 1 minus 0, 1. 1 times log of b over a. A and b are both positive. So this time we're fine, right? It's legitimate.